Welcome everyone. Today, we'll dive into the fascinating world of the Möbius inversion formula and see how it helps us recover important arithmetic functions. Last time, we proved the key identity that convolving mu with the constant 1 function gives the epsilon function, which is 1 at n equals 1 and 0 otherwise.
So we know mu sort of cancels those divisor sums, but we have not yet turned that into a general formula we can use, right?
Here is that fundamental identity in its divisor sum form. When you sum mu over all divisors of n, you get 0 except at n equals 1, where you get 1. We now treat mu, the constant 1 function, and epsilon as actors inside an algebra of arithmetic functions with this convolution operation.
So convolution is our way of multiplying number-theoretic functions by mixing their values over divisors?
Exactly. Convolution is like a product where each output at n depends on the values of the inputs at all divisors of n. Today, our mission is to take a function g defined by a divisor sum of some hidden f and systematically recover f using mu.
So we are turning that basic identity into a general inversion tool, not just a one-off trick.
Let us set up the exact problem of inverting a divisor sum so we can see where mu fits in. Imagine you only see a blurred version g of some original function f, where each value of g at n is built from all values of f at divisors of n. Here is our basic setup. G at n is the sum of the hidden values f at all divisors of n. We assume we can compute g for every positive integer n, but we do not directly know the values of f.
So f is like the hidden image, and g is what we see after this divisor mixing has happened.
Exactly. The big question is whether there is a universal unblurring rule, and Möbius inversion will give us precisely that.
I am curious to see how the algebra of convolution turns this into a clean formula.
Before we jump into the theorem, it helps to build a mental picture for what this divisor sum operation is doing. Picture a bar chart where the height at each integer n is the value of f at n, giving a sharp profile. Now, g at n is built by pooling together the bars of f at every divisor of n, so information at small d spreads to many larger n.
So g looks smoother, because each n averages or aggregates several f values instead of a single one.
Right. Mu is carefully designed so that when you convolve with it, the extra contributions from unwanted divisors cancel out, and you recover the sharp original f. With that picture in mind, we can now formalize Dirichlet convolution and state Möbius inversion precisely. Let us write down the precise definition of Dirichlet convolution and then state Möbius inversion in its full form. By definition, the convolution of f and g at n is the sum over all divisors d of n of f at d times g at n divided by d. We use 1 for the constant 1 function, mu for the Möbius function, and epsilon for the function that is 1 only at n equals 1.
So convolution behaves like a nice commutative product, with epsilon playing the role of the multiplicative identity.
And the punchline from last time is that mu is the inverse of the constant 1 function under convolution. Möbius inversion says that if g is the divisor sum of f, then f can be recovered from g by another divisor sum where the coefficients are mu.
So we have a forward formula defining g from f, and a backward formula reconstructing f from g.
Now let us see why this inversion formula follows almost mechanically from the convolution algebra. We will prove Möbius inversion by treating everything as an equation of functions under convolution. Start from the relation that g is f convolved with the constant 1 function, then convolve both sides with mu and use associativity to group 1 and mu, which we know gives epsilon, leaving us with f. The hypothesis that g is the divisor sum of f is exactly the statement that g equals f convolved with 1.
We are using mu as the inverse of 1, so convolving with mu should undo the effect of convolving with 1.
Exactly. Once 1 convolved with mu collapses to epsilon, we are left with f convolved with epsilon, and epsilon leaves any function unchanged. So g convolved with mu must equal f. Unpacking the equality g convolved with mu equals f gives the explicit divisor sum formulas we saw a moment ago. Let us highlight the two concrete ways you can write the inversion formula for f of n. Here are the two versions. In one, you weight g of n divided by d with mu of d, and in the other, you weight g of d with mu of n divided by d. Because convolution is commutative, f convolved with mu is the same as mu convolved with f, and that symmetry shows up when you rewrite the sum.
So the second formula is really just a change of variables inside the same divisor sum.
Right. In practice, you pick whichever version makes the algebra or cancellation in your specific problem cleaner. Now we will see Möbius inversion in action by deriving and computing Euler's totient function. Our first major application is Euler's totient function, which counts positive integers up to n that are coprime to n. A classical identity says that n is the sum of phi of d over all divisors d of n, because numbers up to n can be grouped by their greatest common divisor with n. Think of g as the identity function that sends n to n, and f as the totient function phi.
That matches our earlier pattern, where g is a divisor sum of f with the constant 1 function.
Exactly. So Möbius inversion tells us how to express phi of n directly as a sum involving mu and n. In formula form, phi of n equals the sum over divisors d of n of mu of d times n over d, which you can factor as n times a weighted sum of mu of d over d.
So once we know mu for the divisors of n, this gives a very concrete way to compute phi of n.
Let us now compute a specific value, phi of 12, using the inversion formula we just derived. First, list all positive divisors of 12, which are 1, 2, 3, 4, 6, and 12.
Using the definition of mu, we get 1 for 1, minus 1 for 2 and 3, 0 for 4 and 12 because of squared prime factors, and plus 1 for 6.
Now plug these mu values into the formula for phi of 12, multiplying each mu of d by 12 divided by d and adding them up. Written out, the sum becomes 12 times mu of 1, plus 6 times mu of 2, plus 4 times mu of 3, and so on for all 6 divisors.
So the total is 12 minus 6 minus 4 plus 0 plus 2 plus 0, which simplifies to 4, matching the fact that only 1, 5, 7, and 11 are coprime to 12.
This example shows how Möbius inversion turns a theoretical identity into a practical computation tool. Our second example shows how Möbius inversion actually recovers the fundamental identity for mu that we started from. Suppose the constant function 1 is given as a divisor sum of some unknown function f, just like our general setup.
So now g does not depend on n at all. It is just always equal to 1.
Applying the inversion rule, f must be the convolution of the constant 1 function with mu. From our previous lecture, we know that 1 convolved with mu is epsilon, so the only f that works here is epsilon itself. Writing out the convolution 1 star mu at n as a divisor sum gives exactly the statement that the sum of mu of d over all divisors of n equals epsilon of n.
So Möbius inversion and the fundamental identity for Möbius actually reinforce each other.
This closes the circle. The basic identity for mu leads to inversion, and inversion in turn rederives that identity. Let us step back and summarize what Möbius inversion has added to our toolkit. First, we learned to think of arithmetic functions with convolution as an operation that mixes their values over divisors of each n.
Epsilon acts like the do-nothing element for convolution, while mu plays the role of the inverse of the constant 1 function.
The central takeaway is that any function g built as a divisor sum of f can be inverted by convolving g with mu to recover f. We use this to get a clean divisor sum formula for the totient function, and to reestablish the identity that the sum of mu over divisors gives epsilon.
It really feels like mu is a universal undo button for divisor sums, as long as we can recognize the convolution pattern.
To finish, let us try a quick symbolic practice problem and then reflect on what Möbius inversion is really doing. Here is the setup. G of n is defined both as a divisor sum of f and explicitly as n squared. Since G is a divisor sum of f, Möbius inversion tells us that f should be G convolved with mu, so plug G of n equals n squared into that rule.
So f of n should be the sum over divisors, d of n of mu of d, times g of n over d, which is n over d squared.
Notice again how mu provides the exact correction terms so that contributions from different divisors cancel, leaving only the original function f. Writing the answer clearly, f of n is the sum over all divisors d of n of mu of d times n over d squared, which is exactly the Möbius inversion formula with g of n equal to n squared.
It is cool that once we recognize a divisor sum, the recipe for recovering f is always the same. Convolve with mu.
Thanks for watching this. Subscribe to Thinking in Math for more topics. We welcome your feedback, leave questions and suggestions in the comments.